All right, I'm going to try and I hit recording this time. I apologize for those of you in concrete that I just I didn't record until we started getting into the examples. So apologies for that. Um, just to be clear, everybody can hear me? Good. Okay. Let's just get right into it. One thing I did want to mention, and I had it on my announcement slide, but I think I kind of slipped my mind. Advanced registration opens up on Monday for everybody needing to take classes next semester. Hopefully you've been able to get in touch with your advisor in terms of what it is that you need to take. We're here for you. If you need anything, if you got any questions, let us know. But with that, let's just chug right into it. We'll see that we may be able to end class a little early, depending on how we get through this. But today I want to talk and sort of finish our discussion on continuously braced beams, and I want to finish that discussion by talking about how you design continuously braced beams. So let's go back to what we've talked about so far. So we've talked about the maximum flexural capacity, possible flexural capacity of a beam, and that is its plastic moment, which is Fy times Zx. And for a continuously braced beam, that is its capacity. Now, we also looked last time at this table 3-2, which is going to become one of the most critical design aids that we use from here on out. You can look up just the MP values, the ZX values. You can look up the shear capacity and a whole host of other things that we will use very much for design. I want to call your attention to something about how the table is organized. If you go to table 3.2 and you look at the sections, we talked about this last time, but the sections are organized in groups. So like over here on the slide, see how the top, there's a W24 by 62, and then so we've got a group of like 5 sections, and then a group of 2 sections, and then a group of 6 sections. You notice how they're organized in groups. Well, with each group, you should also notice that the top row is bolded. The top row has a bold line. The way that it works is that if you look at that group, the top row is the lightest section within that group. So if we look here at the very, very top, we have a W24 by 62, and then a 16 by 77, a 12 by 96, a 10 by 112, and an 18 by 71. Of those 5 sections, the lightest section is the one on the top, the 24 by 62. So in design mode, I would pick the lightest that I could. So I would go to a particular group, and then I would the bold row. So this is one of those scenarios where it doesn't really matter so much about the design efficiency, the MU over PMN, but what matters is that you're picking the most economical shape. In fact, if you look at table 3.2, you could probably pick out all of the shapes that are bolded. We actually have a special name for those shapes. We call those the economy sections in steel design. Those are the shapes that are very, very commonly used as beams because they are the most efficient beams based on their ZX values. So we call those economy sections in steel design. So just an FYI on the terminology. Now, I also want to call your attention to table 3.3. So table 3.2 is it organizes sections based off their ZX values. If you turn a couple pages, so this starts on page 3-28. It's a short table. It's only like 2 pages. Let's see, table 3-28. You should have W shapes organized by their IX value. So if table 3.2 organizes sections by their ZX values, table 3.3 organizes by their IX values. The reason why we kind of need to refer to this table is we might find ourselves in a scenario where we have to pick our section not based off of its moment capacity or its shear capacity, but based on its deflection requirements. So we might also have to refer to table 3.3. Now, if you look at table 3.3, it's organized in a similar fashion. There's similar grouping. So there'll be a group of like 5 shapes, and then 6 shapes, and then 2 shapes, and then 12 shapes. And they're organized based off their IX values. And most of the bolded rows here also match the ones in that previous table as well. So we'll need to refer to both of these. I've just shown you this one today, but there's really not a whole lot to it. It's literally just going into the tables and organizing all the shapes by their IX value. So it's pretty straightforward. So let's talk about design. How do you design a continuously braced beam? So I have a beam and I want to select the beam. I want to pick the beam. So the first step that you need to do is you need to compute the factored moment. You need to figure out how much moment is on the beam. Now, I want to talk a little bit about self-weight, okay? I say that you ought to assume a self-weight, and I think that common assumptions are like somewhere between like 50 pounds per foot and 100 pounds per foot. The better that you get at steel design and the more steel design that you do, the better you are at making a guess. I'll tell you what to guess on a homework assignment and on an exam, but the more that you do this, the better you get at this. Now, this box over here on the right, I kind of want to talk about this a little bit. Some engineers, they don't even bother with making an assumption of the self-weight. And the reason why is because they don't bother with it during the design phase. The design phase being the initial part of the problem where you're figuring out what beam you need to use. The reason why they don't do that is because they do have to account for it in the analysis phase, so they figure it's like extra work. But I don't really recommend that when you're first starting out with steel design because keep in mind, steel beams are much lighter than concrete beams, so the self-weight doesn't have as much of an impact on the problem as it does in concrete. But I still recommend that you ought to assume a self-weight because if you don't, you run the risk of having to iterate the problem more times than necessary, especially when the problem doesn't have much load on, or when the beam doesn't have much load on it. So I always recommend that you assume something just to account for it and try and reduce your iteration. So step 1 is to compute the required, or the factored bending moment. Step 2 is to compute the required IX based on your deflection limits. Now, be careful with your units on this. Don't forget your conversion factor of 1728. So after step 2, you should have 2 values. You should have an MU, the factored moment on the beam, how much load you're putting on the beam, and then IX, the required moment of inertia to meet live load deflection limits. The next thing that you do is the following. Now this step, it looks like there's a lot of word salad here on the slide, but in all actuality, this step doesn't take very long to do. There aren't really any calcs with this. What you do is you go to table 3.2 and you start off with the moment capacity, okay? You look up a section based on the most economical shape that will resist bending moment. So because we're in continuously braced beam land, we look them up based off the Phi-MP values, and we look them up based off Phi-MP, and we choose the bold row, the lightest row. Now, a while back, I said that you can use table 3.2 if Fy does not equal 50 KSI. You can use it for design too. It's just instead of looking it up based on the Phi-MP values, you look it up based on the ZX values. I'm not going to make y'all worry about that in the class. I just want you to know that you can do that. Also, if Fy is not 50 KSI, you have to compute the shear capacity. But again, shear doesn't tend to be that big of a deal anyways for buildings. For bridges, that's a different story. Now, when you look up a section based off of table 3.2, it is possible that the section here. Let me do my formatting here. Let me make sure that that's clear. Now, when you look up a section based off table 3.2, I'm starting to get a little warning telling me my internet connectivity's messing around. Let me know if I need to repeat anything. When you look up a section based off table 3.2, you're looking at only the strength. You're looking at only the moment. it's possible that you look up a section that's got more than enough moment capacity, but it doesn't meet deflection requirements. If it doesn't meet deflection requirements, what you do is you go to table 3.3 and look up a section based off IX. Don't worry, this seems like it's really involved. It's a pretty quick process. The last thing that you need to do is analyze the section. You need to analyze it based off of its moment capacity, its shear capacity, and deflection. So let's take a look at each one of those. Moment capacity, you really only need to check this if the beam is heavier than what you assumed. If you assumed that the beam weighs 100 pounds per foot and you pick a W21 by 44, you don't need to check this assumption, because if the beam can hold up 100 pounds per foot, it can certainly hold up 44. So you don't need to go back and redo that calc. If it is heavier, then you do. You need to go back and update your moments. Same thing with the shears. You do need to update your shears, but again, you're going to see your shear capacity is just, it's not going to be a problem. I can't imagine a common steel beam design problem where shear is an issue. We're going to check it, but it's just not going to be a problem. Deflection limits, honestly, checking the deflection limits really aren't going to be all that necessary. It's probably a good idea just to make sure you don't have any math errors, but from a philosophical standpoint, there's really no reason to recheck the deflection limits, because there's no assumptions that you need to verify. There's assumptions you need to verify with moment and shear because you assume to self-weight, but not with moments of inertia for the deflection limits, if they're live load deflection limits, I should say, which most deflection limits are. Now, I want to take a second and talk about deflections. It's kind of strange. AISC, well, I guess strange isn't the right word. I guess it's just different. The steel manual doesn't really have any limits on deflections. In concrete design, there are very specific limits. Like if you remember, for those of you that were just in class, we had that table, and if you had immediate deflections and long-term deflections and all that stuff, there was, you looked it up. Here was the limit. The steel manual doesn't have that. If you go back in the guts of the manual, so remember how in tension members we looked at chapter D, and then like in connections we were looking in chapter J. Remember the chapters in the back? Well, there's a chapter L. Chapter L is the chapter on serviceability, and there's a section L2 that is the section on deflections, and that is literally all it says. It says deflections in structural members and structural systems shall be limited to not impair the serviceability. That's it. That's all the manual specifies for deflections. There's no L over 360 or limits or anything like that. There's a reason for that. The reason why the manual doesn't specify deflection limits is because in steel design, the concept is they want to leave the specific limit to be up to the client. So if the client wants a deflection limit of L over 600, then that's what you use for design. Plus, steel beams don't crack. They don't experience this like stage loading effect like concrete beams do. So I guess I can understand why you wouldn't need to specify it per se as you would in concrete design. I know that a lot of steel designers would like to have codified limits in the code because it's a liability issue. They don't have to say, well, I just guessed a limit. It was there in the manual. Now, one thing I will mention, AISC, and you all ought to honestly avail yourselves of this before you graduate. If you're a student member of AISC, you have the ability to download a series of design guides that AISC publishes for free. And so these design guides are really intended to cover topics that we don't really have time to cover in typical undergraduate engineering courses, but are topics that you might deal with in professional practice. Like for instance, Design Guide 9 is the design guide for torsion. So if you have a member that's twisted, how do you handle that? And we really don't cover that directly in undergraduate steel. We talk about twisting, but we don't design for it per se. Design Guide 3 is the design guide for serviceability considerations for buildings, and it has a whole host of tables on if you're looking at ceilings and partitions, if you're looking at roof members, cladding, components, and there's all these tables of deflection limits that you ought to consider. I just want you to be aware of it. The gray box that's on the very top of the slide is what's most important. For the purposes of the class, I'm just going to give you the deflection limits, much like a client would. So if I have a beam, I'm going to say design it for this deflection limit, and that's how we're going to do it. So you don't have to look this stuff up. I just want you to be aware that these guides are there. But honestly, if you all, the student member access is free, and they have a lot of really good stuff that's worth downloading on their website. So I would check it out. I want to get into a design problem. We have a continuously braced beam, and we're going to design this beam. So we're going to select the lightest beam possible. We're going to assume a self-weight of 50 pounds per foot. The dead load that's shown here does not include the self-weight of the beam. So that 1.2 does not include the self-weight. We're going to have to add that in. For this design, we're going to ensure that the beam meets a live load deflection limit of L over 600. And so I've got a simply supported beam with a uniformly distributed dead load, but I threw a point load at midspan just to shake things up a bit. So we're going to design this. Let me stop my share and bring up the screen. Okay, let me grab my notes real quick. I printed them off here just a second ago. Hold on. Let me grab these right over here. Okay. All right, so we're going to get right into it. Let me move some stuff around. My desk is getting more and more messy these days. Got to set my surface down like so. Okay, so we have a beam that is a continuously braced beam. We're going to design it as follows. Let me make this a little bigger so it's a little easier to read. Okay, so let's look at a couple things. So let's look at each of these forces, and let's see if we can do our analysis in a somewhat straightforward fashion. So let's look at moments and shears. And what I'm going to say is that our W naught is 50 pounds per foot, or 0.05 kips per foot, and that's assumed. All right. Now, for our self-weight, we have our moment. It's a simply supported beam, uniformly distributed load, so W naught L squared over 8. So that's 0.05 kips per foot times 35 feet squared over 8. And so that comes out to be, actually, I don't have that written out. Give me 1 second. $7.656. And our shear is WL over 2. All right, and I guess I never really specified this out, but whenever I use a sub naught, like the sub O, that's like I call it like the original weights, like the self weight. So whenever I have a sub 0, that's what I mean by that. So 0.05 kips per foot, 35 feet over 2. So that is 0.87. 0.875 kips. The dead load, I guess I'll go ahead and, since that's up there, let me put the dead load is 1.2. So MD WDL squared over 8. This part will get a little repetitive, but that means it's pretty easy. Oh, you go away. And then our VD. This is 21 kips. Now, for the live load, this one's different. Okay, the live load, remember that was a point load at midspan. Okay, and the point load at midspan was 40 kips. Okay, so what you can't do is you can't turn that into a distributed load and then do WL squared over 8. I mean, think about it from a bending perspective. If you have a beam, what's the worst case scenario? Lumping the load right in the middle of the beam or spreading it out? It's lumping the load right in the middle of the beam. So if you turn it into a distributed load, you're spreading it out. So that's unconservative. So don't do that. So ML is PL over 4. And again, that comes from just the table in the back, table 3-23, if you're wondering where these formulas come from a point load at midspan. So that's 35 feet over 4. That equals 350. And then VL is PL over 2. All right, I went through that a little fast. I'll give everybody a sec to catch up and see if anybody has any questions, but I'll give everybody a sec to catch up. Yeah, I might be going through the analysis parts a little fast in class, but again, I feel like a lot of this is a little repetitive, so it's all right to do that. Here, actually, let me set that there. And again, during chat, if you need me to slow down or to go over something, again, please don't hesitate to ask. That's what we're here for. All right. So if we've got that, we can factor the load. Say factored load. So MU is 1.2 times our 2 dead loads. So I'm getting ahead of myself. Okay, and so this, when you plug and chug this, it comes out to be 789.69. And we'll go ahead and compute VU just for the heck of it. Again, it's sort of a formality, but so 58. Oh, sorry, hold on. That's me getting ahead of myself. So 1.2. And so when you plug and chug that, that comes out to be that. Whew. A lot of repetition, but what I'll do is I'll say this. Step 1 yielded the following. MU is 789.69 foot kips, and VU is 58.25 kips. So let me redo that. Kips. I'll give everybody a sec to catch up on that. While everybody's catching up on that, I'm going to pull something up in the manual because I think this would be a good thing to include, because I don't want to just magically come up with formulas. I want everybody to see where I'm coming up with them. Give me 1 second. This manual is a little, it's nice to have digitally, but it's a little clunky, the interface, and so it can take a little while. So I apologize. There we go. Okay, let's screen capture this. Perfect. Okay, so now what we're going to do is we're going to look at the deflections. So first off, let me move this a bit and make it a little bigger. So step 2 is to compute the required IX. Now, we have a live load deflection limit in this problem, if you remember, of L over 600. So I'll put that over here. I'll say that our max live load deflection was L over 600. Now, I got this from the manual. This is on page 3-210. Remember, this is the table that provides the various moment shear and deflection formulas. So some of these formulas you should recognize. So for instance, we've got the maximum moment is PL over 4. So we just used that. The maximum shear is P over 2 because that's what we're getting on our shear diagram. But what I'm interested in right here is this formula, the maximum deflection. So for a beam with load at midspan, the live load deflection is PL cubed over 48 EI. Okay, that's our live load deflection formula. Okay, and our limit is L over 600. So how this is going to work is all I'm going to do is I'm going to solve for I. Okay, so I'm going to say that PL cubed over 48 EI. And then don't forget, we're also going to include a 1728 here. I'm going to say that that's equal to L over 600. Okay? And then I'm just going to solve for I. So what do we got? So we'll say IX required is going to equal the following. It's going to equal, so what do? I can multiply I on the other side. Well, actually, let's not skip this. Let's not do this quickly. Let's take our time with it. So PL cubed times 1728 over 48E is L over 600 times I. Just all multiplying both sides by I, so pixels on the left. And then we'll flip and multiply that fraction over here. So PL cubed 1728 48E 600 over L is I. So does everybody see what I'm doing? I'm just solving for I. So therefore, IX required is the following. And note if you look at the formula, we can actually cancel L's, and that becomes L squared. So we've got PL times L squared times 1728 times 600 over 48E. So L is 35. And then don't forget 29,000 KSI. Now I don't want this to just be me reading off, so somebody tell me what they're getting for this. Actually, hold on. I think I might have a little bit of a boo-boo here. I think I might have a little bit of a boo-boo here. Let me see. Yeah, I have a little bit of a boo-boo. All right, let me explain. Apologies for that. Because that came out to be much larger than needed. Ultimately, what we did is we canceled one of our L values. So because we canceled one of our L values, I apologize. I forgot to mention that ends up being 144. So I'm actually going to do this a little bit more in depth here in a second, but that ends up being 144. My apologies for that. When you plug and chug this out, it should be 3 0.38 inches to the fourth. So let me show you why. My apologies for that. I'm sure that was probably a little confusing. That probably wasn't the smoothest transition. Let me show you what happens with the formula without the unit conversion and explain why it's 144. So here we'll sort of do like a redo. All right, redo. So IX required is PL L squared times 600 over 48E. Okay, now that's ignoring that conversion factor and just assuming everything is consistent units. Okay, so when you chug this out, what happens is this: you get 40 kips times 35 feet squared times 600 over 48 times 29,000 KSI. See, what happened was because we canceled one of those lengths, we actually canceled one of them in our conversion factor as well. Now, let's just chug this value out, like calculate this out, and I'll show you what you get. So if you take this, just raw plug and chug those values, you get 21.12. But let's look at our units. Okay, so we have on the top kips times feet squared over kips over inches squared. So this is 21.12 kips feet squared, and then inches squared over kips. So this is 21.12 feet squared, inches squared. Now, this is a moment of inertia, so the moment of inertia needs to be in inches to the fourth. So we need another inches squared on the top. We need to get rid of that feet squared, and the way that we do that is 144. But my apologies on that. I know that was probably not the clearest. And so 144 is 3041.38 inches to the fourth. If there's anybody that has any questions about that, please, don't hesitate. All right. So the real guts of what I want to talk about today is what happens after that, though. So let's go on to step 3, and let's select a section. All right. This is, I think, probably the most important part. All right. So remember, at the end of step 1, we got an MU of, what was it? 789.69 foot kips. And then we also got an IX required of 3041.38. All right. This is what I want you to do. Let's go to the manual. Let's go to our ZX tables. And I want somebody to help me out with the ZX tables. What would be the lightest section that you would pick based off of MU? So what we're going to do is look up lightest shape with a PMP greater than or equal to 789. help me out. What is the lightest section here that has phi and p greater than that? Everybody in chat, help me out. So we're in table 3.2. I'll go ahead and tell you we're on page 3-24. Okay, so I'm hearing 18 by 9. Okay, so now a lot of people are saying 18 by 97. Okay, but look at the 18 by 97. So you picked that because it has a phi MP of 791, right? Now look at the next row that's bolded above it. What's the bold row above that? Well, the shape though. You're right, it's the 840, but what's the shape? The 24 by 84 is exactly right. Here's the point. The 18 by 97 is the row that has the shape that's just over 789. But why would you pick a W18 by 97 when you could pick a W24 by 84? The W24 by 84 is lighter. It doesn't use as much steel. The 24 by 84 is 80 pounds per foot. The W18 by 97 is 97 pounds per foot. So if I was beam, I'd rather buy the W24 by 84 since it's less money. So this would say try a W24 by 84. Okay. Now there's a little bit of a problem though. All right. What is this for the W? We said that this was 840. But what is that? What's this for the W24 by 84? You don't need to keep in mind, you don't need to go all the way to table 1.1. It's in table 3.2. And you got 2370. What does this mean? You're exactly right. We can't use this because it's less than our IX required. So what we've got to do is we've got to go to step 4 and visit table 3-3. So now what I want you to do is I want you to go to table 3-3 and pick a section based off the IX. Now remember, our IX was 3041.38. So I'll go ahead and tell you I'm on page 3-28 and 29. Our IX required for this problem was 3041.38. A W30 by 90. That's exactly right. I want to make sure that everybody's comfortable with what I'm doing because there's not much response in chat, and I want to make sure that what we're doing is right. So I'm on table 3.3, and if you look at the bottom of table page 3-28 on the bottom right, we're selecting the first bold row that has a moment of inertia higher than that, and so that's a W30 by 90. Now, somebody else other than Mr. Schwartz and Mr. Walker, because you all have been monumentally helpful. Now, I'll go ahead and tell you that IX for this is 3610. Now, somebody go back to table 3.2 and tell me what this is for the W30 by 90. Somebody other than Mr. Stratton. It's exactly right. Now, somebody else other than Mr. Stratton. So first off, all right, hold on. So this is 1060 foot kips. So it's larger than MU. So this is a good trial shape. And while we're at it, somebody other than Mr. Stratton, tell me what's VVVN. $374. It's exactly right. So now we've got a section that's worth looking at. Okay, we're running a little short on time, so I'm going to go through the analysis step pretty quickly. Sorry. So, now remember, let's go back to what we did before. The assumed self-weight was 50 pounds per foot. Somebody tell me, what's the actual self-weight of a W30 by 90? I promise you, it's not a trick question. There you go, it's 90. So because it's heavier, what we have to do is this. We have to go to our M naught and update it because it's now a heavier value. If it was the other way around and our beam was lighter than what we assumed, we really wouldn't have to do any of this. But we have to update this value. This ends up becoming 13.78 foot kips, and V naught becomes 1.58 foot kips. Now, remember that MD was 183.75. ML is 350. VD is 21. And VL was 20. This is what we did in that last step. Oh, yep, it is. So, therefore, our MU is 1.2 M naught plus MD plus 1.6 ML. So we basically redo this calculation with the new weight. And so the moment changes a little bit. It becomes 797.0 foot kips. And the same thing with the shear. It changes a little bit. V naught plus VD plus 1.6 VL which is 59.09 kips. And remember, we'd compare this against MPX, which was 1060, and VNX, which is 374. So again, more than enough shear capacity. Shear capacity is never a problem really with steel beam design in buildings. Moment capacity, we knew we were good from step 3, but we had to pick a heavier section because of the deflections, and we know the deflections are good because we really don't have to go like that. So use a W30 by 90. All right, let me pull this up real quick because I want to show you something before we leave. We are running short on time. I'm going to tell you what, this is what I'm going to do because the deflection calcs that we did in step 2, I get the feeling they might have been a little confusing, and that was probably on me because I did it a little differently than I normally would do. I think I cut some corners, and I'd prefer that a little differently to make it a little clearer for you. So what I'm going to do is this. First thing I'm going to do is I want to pull up the homework assignment. So here's the homework assignment. I kept everything simply supported and uniformly distributed. What I'm going to do is later on today, I'm going to download all the videos from this week and make sure that they're on the YouTube playlist. And then I'm going to upload another like 5-minute video talking about not only the deflections that we did for the in-class example, but I'm going to talk about deflections for this beam and show you a simpler way of doing it. I think I probably overcomplicated it and made it a little more confusing than it needed to be, and I'm really not wanting to do that given our scenario. So I'm going to make that deflection calc a lot more straightforward. And I'm going to post that probably like here in the next couple of hours. So I do apologize if that was confusing. If there's any questions though about other stuff, I can answer those. We still have a few more minutes. Well, I'm not getting any questions. Let me say this. If you all have any questions about this homework assignment, I mean, please don't email me or you can send a message through Teams or anything like that. Like I said, I'm going to post another video to clarify the deflection calcs because I think what I did was probably a little bit more involved than it needed to be. So I'll simplify that for you. Don't worry. That's all I have, everybody. What we're going to do next time is we're going to move past continuously braced into discretely braced beams. I think you're going to find they're a little bit more involved, but I honestly find them to be a lot more fun. But that's just me. But then again, I really like this stuff. Hold on. You don't have to redo the MO and VO calcs if the actual weight is less than the assumed weight. That's exactly right. You just use the MU and VU from step 1 because there's really, I mean, you could if you wanted, but you know that it can hold up the weight because if it can hold up 50 pounds per foot, it can certainly hold up less than that. But you're exactly right. You just use the MU and VU from step 1. Any other questions? What? It says you lowered your, oh, there you go. Oh, I see. You have a question, Mr. Schwartz? I will wait. Is there a possibility? So you're saying it. So are you saying that if you assume like 100 pounds per foot and the section ends up being like a W14 by 22, that the like if you assume too heavy a value, could your section not be as economical? Um, that's possible, but in building design, there'd have to be a big discrepancy between your assumed self weight and your actual self weight for that really to be an issue. That can become a situation in bridge design, but the loads that we're dealing with are far higher in bridges. The reason for the assumed self weight is really to make sure that you don't have to iterate too much on the lighter side of beams, not the heavier side. So I guess to answer your question, yes, there's a possibility, but it's very, very remote in our real life scenarios. And again, if the assumption of self weight becomes like cumbersome, you can simply not assume a self weight. The only thing that that does is if you don't assume a self weight, you might pick a trial section and then analyze it and find it's no good, and then have to pick the next one. It might be a more comfortable approach for you. I just think on the lighter side of things, it causes a little bit more iteration than needed. Any other quick questions I can answer? All right. Well, like I said, I'm going to download this to YouTube and post a little clarification on that deflection problem, and hopefully that'll clear things up a bit. And I'll get your homeworks graded also as soon as I can. That's all I got, everybody. I will see you all on Monday. You all have a wonderful weekend.